talk, please let me just tell you that please feel free to stop me at any point and ask me questions. Okay. So in the past 2 decades, our world has entered the era of big data. The information technology industry is now faced with both the challenges and the opportunities of processing and analyzing massive amounts of data on a daily basis. Both the size and the dimension of the data has reached an unprecedented level and is still growing at an unprecedented rate. So if you want to keep an example in mind, then consider that in YouTube, around 300 hours of videos are uploaded each minute. In Facebook, around 300 million photos are uploaded each day. Even on the scientific front, super resolution microscopic imaging technologies have undergone tremendous advances and are able to generate more large numbers of images with subatomic resolution. Similarly, high throughput gene sequencing technologies are able to sequence hundreds of millions of DNA fragments at a time. Now, although we are in the data rich regime, it does not necessarily mean that we are in the information rich regime, or at least not for free. This is because massive amounts of data are being collected today without having a specific goal in advance. And therefore, for any new task, it is possible to overwhelm the practitioner with a large amount of data that might contain a lot of irrelevant or redundant information. So let me give an example. Consider the two images that are being shown here in this slide. The image on the left has 2500 times 2500 pixels. And therefore, if we write it out as a vector where each pixel is a coordinate, then this vector will be an extremely high dimensional one. On the other hand, the image on the right only has 250 times 250 pixels, and therefore it resides in a much lower dimensional space. However, to the human eye, there is hardly any difference between the two images, and therefore clearly the identities of the two adorable girls in the images depends on significantly lower dimensional statistics. Hence, we can conclude that high dimensional data points, such as the left-hand side image, often has a significant amount of redundant information. For example, a set of redundant pixels in this image. And moreover, such high dimensional data points also has a hidden structure. For example, the set of relevant pixels in the left-hand side image. And if it is possible to recover this hidden structure, then we can design algorithms for more difficult tasks on a significantly lower dimensional space. And therefore, those algorithms have the potential to be much more efficient. So how can we design scalable algorithms for learning and inference under such settings? The approach that we consider is to carefully choose a class of machine learning models that satisfies several properties. First of all, each member of this parameterized class of machine learning models must have a small number of learnable parameters so that it is possible to design algorithms with a low data complexity and a low computational complexity. However, at the same time, this class of machine learning models must be powerful enough to closely fit complicated functions that might arise in practice. Moreover, this class of machine learning models must also incorporate some structural properties that are very likely to be satisfied by real-world datasets. So what can be examples of such structural properties? While there have been quite a few that are studied in the literature, in this talk, I'm going to focus on two of them in particular. First of all, we're going to assume that the data set has latent clusters. That is, the set of data points can be partitioned into clusters which are unknown, but each cluster is in some sense simple. So what does this mean? In the unsupervised setting, this might mean that a simple and well-known or well-studied distribution such as a Gaussian or a Poisson can be used to model the data distribution restricted to each cluster very closely. In the supervised setting, this might mean that a simple function such as a linear one, can model the relationship between the target variable and the feature variables very closely when restricted to the data points in each cluster. We can model this phenomenon by assuming the data points are generated from a mixture of simple models. Furthermore, we are also going to assume that for each cluster of data points, only a few features contain relevant information. Of course, the features that contain the relevant feature information are going to be different from cluster to cluster. We can again model this phenomenon by assuming that each simple model in the mixture is parameterized by a sparse vector. So by combining these two structural assumptions, we are going to look at a data generating mechanism that we can call mixture models with sparse parameters. And in this talk, we're going to focus on the unsupervised setting. So let me informally describe how the data generating mechanism works. That is how we can generate samples from a high dimensional mixture of distributions. Okay. So suppose we have two distributions, distribution 1 and distribution 2, and each of them are parameterized by sparse unknown vectors. Now, in order to generate samples from a mixture of these two distributions, we're going to do the following. For each sample, we are going to toss an unbiased coin. If the coin lands heads, then conditioned on this outcome, we are going to generate the sample from distribution 1. If the coin lands tails, then conditioned on this outcome, we are going to generate the sample from distribution 2. So for the first sample, suppose the coin landed heads, then conditioned on this outcome, we generate the first sample from distribution 1. For the second sample, the coin landed tails, and therefore we generate the second sample from distribution 2. Similarly, for the third sample, the coin landed heads again, so the third sample is generated from distribution 1. Now, I must emphasize over here that we observe only the set of samples. We do not observe the outcome of the coin tosses. That is, we do not know which of these two distributions was used to generate each sample. However, our goal is to use the set of observed samples to learn something about each of the sparse unknown parameter vectors governing the two distributions under the assumption that the samples have indeed been generated according to the mechanism that we have just described. So mixture models are not new at all. In fact, they were introduced in 1894, and since then, they have become a very powerful tool in the statistical toolkit. So let me motivate mixture models a bit from the point of view of a very canonical problem in machine learning, namely distribution fitting. Suppose we have a real world data set and we want to fit a distribution onto this real world data set. Now, a very popular choice for a family of distributions that we can use to fit the data set is a family of Gaussian distributions. This is because Gaussians have several properties that are very likely to be satisfied by real world data sets. For example, Gaussians are symmetric in nature, having the same mean, median, and mode. Gaussian distributions look very much like a bell curve, which are often observed in real world data sets. Also, Gaussian distributions are parameterized only by the mean and the covariance, and therefore, if we fit a Gaussian distribution, it lends a lot of explainability. However, Gaussians are not well equipped to model data sets that are skewed or asymmetric in nature. Let me give an example. Okay. Suppose we have a data set where each data point corresponds to the height of an adult. If we plot the histogram of such a data set, then it will look something like this black curve over here. And clearly this black curve is asymmetric or skewed. And therefore, if we try to fit a single Gaussian distribution onto this black curve, it will not be a good fit. The best fitting Gaussian will not be able to model the properties of this height dataset at all. However, it turns out that such a dataset has latent clusters. If we aggregate the data points that correspond to men and plot the histogram of the heights corresponding to men, it will look something like a bell curve, which is shown by this blue line. Similarly, if we aggregate the data points corresponding to women and plot the histogram of their heights, it will also look something like a bell curve, shown here by this red curve. Therefore, it turns out that if we fit a mixture of two Gaussians onto this data set, it will be a really good fit. Therefore, mixture of Gaussians are quite flexible and powerful. It can not only fit unimodal asymmetric distributions, but it can also closely fit many other naturally dense occurring density functions for which a single Gaussian is clearly not enough. In particular, for all the density functions that have been shown here in this slide, it turns out that a mixture of Gaussians with a small number of components and therefore a small number of learnable parameters can fit each of these density functions very closely. For instance, if you look at the claw density function, which looks very much like a claw, it turns out that a mixture of Gaussian with only 5 components is able to model the claw density function quite closely. And due to such expressiveness and representational power, mixtures of Gaussians and mixtures of distributions in general have found applications in many different fields, including astronomy, biology, genetics, medicine, economics, engineering, etc. However, the primary difficulty in learning mixture models is the presence of latent variables. We do not know which particular component of the mixture was used to generate each sample. And this lack of information
can you hear me?
Yeah.
Question
Yeah, of course.
So is there a theorem which, if we were to look at all classes of mixture of Gaussians, is it in some, it's probably dense in some class. So is there a theorem which kind of shows light on this?
All mixed, sorry, can you say that again?
Yeah. Let's just take the real line and let's look at mixture of Gaussians on the real line.
Okay.
Now, can we model any distribution arbitrarily closely, or can we model some class of distribution arbitrarily closely? Is there a theorem of that sort? You know?
Oh, that's a good question. I do not exactly know of such a theorem, but my advisor did point out to some results of this sort.
Okay.
I can get back to you with the answer to this. It's a good question.
Sure.
Yeah, I mean, if you allow for an arbitrary number of Gaussians, then I would imagine that you should be able to. I mean, that would be my guess.
Yeah, with a finite number of components, I think there has to be some kind of restriction. But
yeah. Okay. Cool.
I see. So, okay. But there should be a theorem of that sort, right?
Yeah, definitely.
All right.
Okay. Yeah, so this lack of observations, that is, which component was used to generate each sample, is what makes learning mixture models challenging. Now, there exists vast literature on learning mixture models with theoretical guarantees, and let me give a brief snapshot of it. However, I must point out that literature is quite recent, given that mixture models were introduced in 1894. Now, the theoretical guarantees that exist are mainly of two flavors. The first one is called parameter estimation, where the goal is to estimate the underlying parameters of a mixture from the samples. And in this regime, the first result was provided by Sanjay Dasgupta in 1994 in a seminal paper where he proposed a simple clustering algorithm and showed theoretical guarantees under certain assumptions on the gap between the component parameters of the high-dimensional mixture. And this was followed by a series of works which improved the clustering algorithm by relaxing the gap assumptions and culminated with the work by Vempala and Wang in 2004, who showed that it is possible to project the high-dimensional samples of the mixture onto a very carefully chosen lower-dimensional subspace and then apply the clustering algorithm. The technique almost got rid of the gap assumption. However, truly gap-free algorithms were first introduced by Kalai, Moitra, and Valiant in 2010, again in a seminal paper, by using the method of moments. This was again followed by a series of work who extended the technique of method of moments for proving sharper results in mixtures of Gaussians, and also extended them to mixture models in the supervised setting, such as mixtures of linear regression and mixtures of linear classifiers, where tensors were used to estimate the mixture parameters. More recently, there has been a series of works on theoretical guarantees for practical algorithms such as alternative minimization or expectation maximization, which are used to fit mixture models onto real-world data sets. And finally, in my thesis, I have introduced a new technique based on lower bounding the total variation distance between any two mixtures. Okay, and interestingly, it turns out that such a characterization of the statistical distance between any two mixture distributions can be translated into sample complexity guarantees for learning a mixture from its samples. The second flavor of result is known as density function, where the goal is to fit a density function onto the set of samples such that the output density function is close in some statistical distance to the ground truth distribution. Proper learning is when the fitted density function is constrained to be in the same class of parameterized model as the ground truth distribution. Improper learning, there is no such constraint. So in this talk, I'm going to look at a different flavor. That is, I'm going to look at support recovery, where the goal is to learn the non-zero indices of the individual sparse parameter vectors parameterizing the mixture model. Okay. So the outline for the rest of the talk is going to be the following. First, I'm going to more rigorously define the mixture model and the problem of support recovery. We're going to look beyond mixtures of Gaussians, and in fact, we're going to study mixtures of many different high-dimensional distributions, such as Laplace, uniform, exponential, etc., with sparse unknown parameters. And for the problem of support recovery in mixture models with sparse parameters, I'm going to show a set of very new and generic techniques, and we will see how it can be applied for support recovery in mixtures of distributions. However, our techniques are very generic. It can be applied to mixture models in the supervised setting as well, such as mixtures of linear regression and mixtures of linear classifiers as well. Finally, I will end with a conclusion and some open problems about which I'm really excited. So let me be a bit more mathematically rigorous. Consider a class of simple one-dimensional distributions, okay, denoted by curly p, each of whose member is denoted by p of phi and is parameterized by a real number phi. So curly p is just a family of simple one-dimensional distributions. So let's look at some canonical examples of curly p. So curly P can be a family of one-dimensional Gaussian distributions parameterized by the mean with known variance. So each member, P of phi, can be a Gaussian with mean phi and variance sigma square, as sigma square is known. Curly P can be a family of exponential distributions parameterized by the mean. So P of phi can be an exponential in phi. Curly P can be a family of uniform distributions parameterized by the starting point of range. So P of phi can be a uniform distribution starting at phi and ending with B, where B is known. Okay, so let's fix such a family of one-dimensional distributions curly P. And given this family, let me define a mixture of high-dimensional distribution. Now, suppose we have fixed such a family, the curly P, which is known. Now we have a set of unknown sparse parameter vectors, theta1, theta2 up to theta l, which are d-dimensional. Each sample vector x is generated according to the following process. First, we generate a latent variable t uniformly at random from 1, 2 up to l. And given the latent variable t, the ith coordinate of the sample vector x is generated from the distribution p, which is a member of the family curly p we have fixed. And the distribution p is parameterized by the ith coordinate of theta t. Okay? And we are further going to assume that all the coordinates of the sample vector are independent given the latent variable t. Now, this strong assumption of independence is not necessary and can be relaxed significantly. However, let's make this assumption for the sake of this talk. Okay. So any questions at this point about the generating process?
So I guess all are the same, right? For every so theta 1 to theta L have all at the same P.
Theta 1 to theta L all have the same.
So you cannot have one Gaussian and one exponential. They're all either
Oh
Gaussian.
yeah. So we fix a family curly P.
Yeah. Okay. Yeah.
So we
Okay.
fix a family curly P and then we generate the samples. We assume that the family curly P is known.
And
Yeah.
theta 1 to theta L are known to you. You just don't know when you look at the data, you don't know which theta it is. But you know that it's one of these L.
So theta 1, theta 2, and up to theta L are also unknown to me.
Oh,
These vectors are unknown to me. I know that they are sparse and I want to recover their support.
You know L or you don't even know L?
I know L. I know L. So
No.
L is assumed to be known. That is, the number of components is assumed to be known. So here the latent variable is T is unobserved. Okay, so given T, we generate each coordinate according to the one of the simple one-dimensional distribution.
And your aim is to recover theta T.
Yeah, all this theta, support of all these vectors, theta 1, theta 2 to theta n.
I see. Okay.
Right. Right. So given so basically the latent variable fixes the vector theta according to theta t according to which the sample will be generated, and given the ith coordinate is generated according to distribution p parameterized by the ith coordinate of theta t. Okay. So let me give an example. Perhaps it will make this clearer. Suppose we fix curly P to be the family of simple one-dimensional Gaussians, so that each member P of phi is just a Gaussian with mean phi and variance sigma square. Okay. Now we have these two unknown vectors, theta 1 and theta 2, which are sparse. And if we have such a setting, then our samples are basically generated from a mixture of two high-dimensional Gaussians. One of the Gaussian has mean theta 1 and covariance identity. The other Gaussian has mean theta 2 and covariance identity. So we generate samples from a mixture of these two high-dimensional Gaussians. That is, in order to generate each sample, we first uniformly at random pick one of these two distributions, and then conditioned on it, we generate the sample from the chosen high-dimensional Gaussian.
So, Soumyabrata, in your setup, these this uniform distribution that you're assuming, or you're allowing weights to be arbitrary?
For now, I'm assuming that a uniform mixture actually.
But that's not critical, or it is important?
It's not critical, but in the paper I've analyzed the uniform mixture for simplicity, but it's not critical.
Okay.
So
do you know the sparsity? Do you know the sparsity parameter? Like how many of the elements are zero in each theta?
Right. Yes, that is also assumed to be known, but we can take an upper bound is also sufficient.
Okay, thanks.
Thanks. So our goal is to recover the support of these two parameter of the unknown parameter vectors. That is, we want to find the non-zero indices of each of the unknown parameter vectors. So our algorithm should basically return, in this example, two binary vectors, z1 and z2, such that the position of the ones in one of the binary vectors correspond to the position of the non-zero indices in one of the parameter vectors, and position of ones in the other binary vector corresponds to the position of the non-zero indices in the other parameter vector. So here z1 basically corresponds to the support of theta 1 and z2 corresponds to the support of theta 2. And our goal is to recover z1 and z2.
So why are you not looking for values and only for positions?
Right. So support recovery is supposed to be an easier problem. We should think of it as feature selection, where you are basically finding out the important features. And if you can solve this easier problem, then you can actually solve more difficult problems like finding out the values or parameter estimation, as the problem is called. Uh, we can try to design algorithms for parameter estimation that can be potentially much more efficient.
Mhm.
Okay. So actually, I have a slide on this. So why support recovery? Sorry. Support recovery is a very well-studied problem in signal reconstruction, but not in mixture models. And however, many high-dimensional datasets have sparse learnable parameters and latent clusters. And as I already said, that you should think of support recovery as a feature selection. If you can solve the support recovery problem, which is supposed to be an easier task, although it still suffers from the problem of latent variables, then you can not only gain deep insights into the problem, but also you can potentially solve more difficult tasks such as parameter estimation and with algorithms that have the potential to be much more efficient. Now, note that we want to solve the problem of support recovery with a very small number of samples that scales polylogarithmically with the dimension. It should not scale linearly with the dimension. Okay, we want the sample complexity to be only polynomial in the sparsity, say, just like polynomial in the sparsity or even polylogarithmic in the sparsity, which is even better. So mixture models with only a few relevant features have been studied in a few other papers, but they consider a slightly different model. So let me state my result, and perhaps that will make this more clear why support recovery is important. So in many different problems of mixtures of high-dimensional distributions with sparse parameters, it turns out that we can recover the support of the unknown parameter vectors by only using a samples that scales polylogarithmically with the dimension and the sparsity. Okay, so our sample complexity is very small. It's just polylogarithmic in the dimension. Here, rho tilde notation hides some factors in the number of components and other properties of the unknown vectors and base distributions. And our approach to sorry, please.
Sorry, a stupid question. So sparsity is always at most the dimension, right?
Right. That's exactly correct. So we should think.
Yeah.
We should.
Yeah.
Exactly. So we should think of the sample complexity to be essentially independent of the dimension.
Yeah.
But the polylog factor might be different for the dimension and the sparsity. But
Oh, I see. Okay, that makes sense. Thanks.
yeah. Okay. And our approach to solve this problem is to use the method of moments. And our results hold for mixtures of many different high-dimensional distributions, including Gaussians, Laplace, Poisson, etc. So let me show our techniques for support recovery, and which I've already said are quite generic. And we will also see how we can apply them to mixtures of distributions. So in order to introduce our techniques, I will start with a definition, which is quite simple. So consider a set of sparse vectors, θ1, θ2 up to θl. Then S of I is the set of vectors having non-zero value at index I. Okay. So let me give some examples to make this definition clearer. Suppose you have these two sparse vectors again, θ1 and θ2. Then if you look at the first entry, only θ1 has a non-zero entry in the first index. So S of 1, which is the set of vectors having a non-zero entry in the first index, is just going to be the vector θ1. If you look at the first and the second index, then only the vector θ1 has a non-zero entry in the first and the second index. So S of 1 intersection S of 2, which is the set of sparse vectors having non-zero entries in both the first and second index, is just going to be θ1 again. If you look at the third index now, then both θ1 and θ2 have zero entries at the third index. So S of 3, which is the set of sparse vectors having non-zero entries in the third index, is just going to be the null set. Okay, so for a given subset C of indices, the cardinality of the intersection of S of I, where the intersection is over all the indices in C, corresponds to the number of vectors having non-zero entries in all the indices of C. So now let me present the lemma, which I think I've advertised quite a bit by now. So if you consider a set of unknown sparse vectors, θ1, θ2 up to θl, then if for all subsets of indices C having size less than or equal to some small number t, the number of unknown sparse vectors having non-zero entries in all the indices of C is known. That is the cardinality of the intersection of S of I, or the intersection is over all indices in C is known. Then we can recover the support of all the unknown vectors. So this lemma basically states a sufficient condition for recovering the support of all the unknown vectors. So I will pause a bit at this slide so that you can stare at this lemma briefly, and please ask me any questions if you have any.
Okay, so here's a stupid question. So can we just think of our problem as follows? See, we can maybe assume that if for some entry of some theta I, we have a non-zero parameter, then there is a good chance that our generated sample will also maybe be non-zero. So maybe we can just look at these non-zero guys and use that. So we can maybe completely discard the sample itself and only look at its support.
But if you think of a Gaussian distribution, for example, it will never be zero, right? Even if it has a zero mean.
Okay, yeah, sure. Okay. Yeah, indeed. Okay, so when we talk about, okay, yeah, okay, yeah, now that makes sense. Yeah.
Okay.
Okay,
Yeah.
so it's essentially saying that, yeah, so if you look at Gaussians, for instance, then maybe all of our different entries in the vector have zero mean Gaussians, but some of them are non-zero mean Gaussians. And even for the zero mean Gaussians, their variance can be pretty big, perhaps, maybe it's sigma squared.
Yeah. The variance can be, the variance is obviously not zero.
Okay.
The variance is actually identity, which we have, if we have a high dimensional Gaussians, basically.
Yeah, exactly. Yeah, so okay, so then maybe we could look at a lot of samples and try to average them out. I think that's essentially maybe could work.
That's a good point. So the problem with that is, suppose you have a mixture of Gaussian, where theta, mixture of two Gaussians. Let me just go back to the slide. Yeah, so if I have samples that are being generated according to this mixture, where θ1 is exactly equals to minus θ2.
Oh yeah, then the whole means become zero, kind of.
Yeah, you will not be able to find it in this way. And this is what makes the problem challenging.
Okay, good. Thanks.
Sure.
So we just can you hear me?
Yeah. Please go ahead.
So this is like saying that if you have enough polynomial equations of small degree in Boolean variables, then you can recover.
Right.
L times.
Right.
The dimension is unknown.
Right.
L times d equal. So you want enough. So LD variables, and you want enough polynomial equations in Boolean variables.
Right.
Yeah. So is some kind of analog of this. I think it's called Chow's lemma or something.
I have to check back on that.
No, that's not that's something that says that knowing the first order Fourier coefficients of half spaces is enough to recover the.
Okay.
But that's slightly different.
Okay. I have to learn about Chow's lemma. Thanks for the pointer. Okay, so one question at this point can be that how small does T need to be? Okay, because the larger T is, you can expect that you will need more and more samples to recover the support. So we can show that in the worst case, T just needs to be log the number of unknown vectors plus 1. And we can prove this by using set of combinatorial arguments. However, under extremely mild assumptions on the unknown vectors, we just need T to be 3. And we can prove this result by using techniques from unique low-rank tensor decomposition. So let's go ahead and actually prove this latter statement. So we are going to show that under extremely mild assumptions on the unknown vectors, T just needs to be 3. So a brief recap of what this means. If we have a set of unknown sparse vectors, then in order to recover the supports of those unknown sparse vectors, for each subset of indices of size at most 3, we only need to know the number of unknown vectors having non-zero entries in all the indices of that subset. Okay. So let me begin by a brief introduction of tensors. So you should think of tensors as multidimensional arrays and generalizations of vectors and matrices. Vectors are basically one-dimensional tensors, matrices are two-dimensional tensors, and the quantity that I've shown here in this slide is a three-dimensional tensor. That is, it has 3 dimensions, namely height, width, and depth. And tensor that I've shown here on the slide has dimensions 5 times 5 times 3. Okay. So now let me define what a rank 1 tensor is. So if you recall matrices, then a rank 1 matrix is nothing but the outer product of 2 vectors. Okay. So the entry in the ijth entry of a rank 1 matrix is nothing but the product of the ith entry of one of the vector and the jth entry of the other vector. Similarly, a 3-dimensional rank 1 tensor can be represented as the outer product of 3 vectors, A, B, and C. The entry in the ith row, jth column, and kth slice of this tensor can be represented as the product of the ith entry of the vector A, jth entry of the vector B, and kth entry of the vector C. Okay. So how does this help us? Okay, so let me give you a very brief definition. For a vector V of d dimensions, let sup of V be the corresponding support vector. Okay, where the sup of V is a binary d-dimensional vector, so that the ith entry of sup of V is 1 if the ith entry of the vector V is non-zero, and the ith entry of the support of sup of V is 0 if the corresponding ith entry of the vector V is 0 as well. Now, the key observation is this equation. The left-hand side, as you probably know by now, is the number of sparse vectors having non-zero entries in all the indices of C. Okay. And interestingly, the quantity on the left-hand side can be written in a nice sum product form, which is shown on the right-hand side. The sum is over all the sparse vectors, and each of the product terms constitutes the product of the entries of the ith support vector at all the indices of C. So clearly, this product term, the ith product term, can be 1 only if the support of the ith parameter of the ith vector has 1 in all the entries of C. And therefore, the right-hand side also corresponds to the number of sparse vectors having non-zero entries in all the indices of C. And therefore, if we know the left-hand side for all subsets C up to a fixed size, then we can aggregate this information, write it out in this sum product form as shown on the right-hand side, and represent this information in the form of a tensor, okay, which can also be represented as a sum of rank 1 tensors, where the ith rank 1 tensor is the outer product of the support of the ith sparse vector done the size of C times. Okay, that is the dimension of each rank 1 tensor is the size of C. And therefore, this
We lost him, right?
Yeah. Okay. I was wondering if it was on my side or yeah.
Yeah, we lost him.
Someone's calling me. So what's this calligraphic A here? Do you know?
Yeah, it looks like a matrix, right? It looks like a tensor, right? So he's doing a tensor of all these everything. So that big tensor is A. Is it adding up all these tensors somehow?
Yeah, I'm just wondering how.
Should be something wrong in the ordering of indices, right? Shouldn't it be like support of theta? So theta is the ith vector, right?
Yeah.
Just doing a tensoring of the same thing C times doesn't seem
The
to do it.
tensoring in the previous one itself. So it's like what was the definition? SI
So
is
I think support is a 0-1 vector, right? With ones wherever. Yeah.
support of theta I j and okay. For each I, okay, I see. Yeah, it's fine. Yeah, it's fine.
Yeah, first one is fine, but second one looks weird.
Yeah.
Yeah, second one you will look at the so you look at the corresponding entry of the tensor, right? Like corresponding to C, I guess. Right?
Yeah, I would imagine.
So somehow his video is also gone now, right?
Yeah, it is. We'll wait for him to come back, right? I guess what else can we do?
Yeah, about the Gaussian question, I think it's called the fact that Gaussians are dense in the so-called short space. So
I see. So what's the conclusion?
So anything in the so-called short space, these are functions whose derivatives decay fast. Like, so basically functions which look like a polynomial times e to the power minus alpha squared. So that's an important plus. Yeah.
But they're not mixtures in the traditional sense. Right? Mixtures should be convolutions of Gaussians with probability measure.
So I think doesn't mixture just mean that you take, it's not convolution, it's just like summation of, so the density is just the convex combination.
Yeah.
But so convex combination is different from what you are suggesting, right? You are suggesting maybe arbitrary linear combinations.
Oh yeah, there's minus signs also allowed. Right.
Yeah.
So if you normalize, then that is probably fine. But let's see. Yeah. So what happens if you have negative?
Yeah, I mean, I think if you're interested in Gaussians with a fixed variance, then there may be some additional structure, because what you're basically asking is what measures are obtained by convolving an arbitrary measure with a Gaussian. So that could possibly have some characterization. But if you're allowing variable length also, then I don't know. The variable variance, then I don't know.
So the question I had in mind was that I have an arbitrary distribution which I want to estimate to epsilon accuracy. Right. So measure on any set should be within epsilons. Maybe say total variation distance or something.
Yes, so that Schwarz thing will give that, provided you could avoid negative things. I guess that's the point.
I see. Okay.
So if you only have positive terms, then anyway, because the probability distribution, you can just normalize, I think. And then,
right. I guess then the theorem would be maybe even more general, right? Not just mixture of Gaussians, but mixture of certain class of distributions.
Yeah. So my
anything will have to have a tail.
linear programming, no? Because this positivity constraint, how are you going to implement? You'll have to use some linear programming.
Okay, what do we do? I'll write a mail to him, I guess. Is there a new link we can send him in case he wants?
I think he's come back.
He's back?
He's not come back now. No, because I am the host, so I should get an invitation, right? If he tries to re-enter. I mean, I should have to say okay or something, but he's not trying to re-enter.
But maybe we can make this like you can re-enter without asking or something.
So you can turn off the waiting room. So if you go to the participants tab, there'll be okay, and at the bottom right there should be some more or something, and you can turn off waiting room.
I don't have this.
Yes, more. And let's see.
Hari, can you write an email to him?
Yeah, one sec. Turn off waiting room. So mute all upon entry, enable waiting room. But waiting room is not enabled.
Oh, then he will be able to join whenever he can.
No, because he's still there, right? He has not he's not disappeared. He's still there. It's just that his video has gone.
Yeah, there's clearly some network issue that he seems to be facing.
Okay.
Yeah. I mean, I can force him out, but I don't know if that will serve is that the right thing to do? But I mean, then he has to come back.
That maybe actually might help.
Okay, let me just.
What do you guys think? What does Ramprasad and Piyush think?
I don't know. I mean, like even if he joins back via a different account, it will show him here twice. So I don't think that is the issue.
Okay. Okay, I'll write him an email.
No, I've written to him. I've sent him my numbers in case there's an issue with him.
I think he left.
Good, so maybe he'll join then.
Oh, now he's back.
You're back. Oh. Can you speak?
I think he's connecting to audio.
Sorry, can you hear me?
Yeah.
Yes, we can.
Sorry, I did not know where I got disconnected. Can you?
That's okay. Can you continue?
You can reshare your screen, etc.
Oh yeah, sorry. Let me just. Okay, can you see my screen now?
Yeah.
So there is a weird echo that I'm hearing. Am I the only one?
No, there is.
Okay.
So can you tell me where I got disconnected?
So are you currently on a different device or something? I mean,
no. I'm not. Is it better now?
Yeah, there is a weird echo. I don't know how to.
There's a slight echo, but maybe we can.
But I guess we just continue. Yeah.
Okay, sorry about that. Can you tell me where I?
So in the previous, this calligraphic A you had not defined in the previous slide. Yeah, this right here is middle line.
Okay. Okay, so I was just saying that. Right. So yeah, if we know the left hand side for all subsets C up to a fixed size, then we can aggregate this information and represent it in the form of a tensor, which is a sum of rank, which can represent a sum of rank 1 tensors. And each of this rank 1 tensor is the outer product of the support of the ith support vector. But the outer product is done the size of C times. So the question is that if we are given this rank 1 tensor A as input, then is it possible to uniquely recover the support vectors from this given input, given tensor A. That is when the size of C is 3. So when the size of C is 3, we basically have a three-dimensional tensor A as input, which is a low-rank tensor. And the question is that if we can recover the support vectors uniquely from A. And to answer this question, we can look at low-rank tensors, which can be represented as the sum of rank 1 tensors. And while each of the rank 1 tensors can be represented as the outer product of three vectors A, B, and C. Now we can, if we look at the matrix world, then a matrix which can represent the sum of rank 1 matrices is nothing but a low-ranked matrix. And interestingly, for low-ranked matrices, it is not possible to uniquely recover its components. This is because if we multiply the components by a rotation matrix, then the product of the components will give you back the same low-ranked matrix. However, things change drastically if we just go to three-dimensional tensors. For a setting of three-dimensional tensors, we can recover all the components, that is the vectors A1, A2 up to AR, B1, B2 up to BR, C1, C2 up to CR uniquely up to scaling if these corresponding sets of vectors are linearly independent sets of vectors. And the algorithm to recover these vectors uniquely is also efficient and is known as generic algorithm. So we can just use this.
Sorry, I didn't understand about the comment about the matrix. I mean, for example, if your matrix, I mean, the singular value decomposition does exactly this for a matrix, right? So why is that not that good enough?
So because you cannot recover them uniquely, right? For example, if you have a singular value, even if you have a singular value decomposition, you can only recover them up to rotation. For example, if you have this, if you have a matrix A equals to UV transpose, for example, then you can.
Yeah, but that is because the singular values are all the same. So if the singular values are all distinct, then of course you get all of them differently. So you cannot separate the eigenspace or the singular value space of the same singular value.
Right. So
that's what you mean, is it?
Yeah.
Okay, yeah, thanks.
Okay. So we can immediately use this result to state that we can recover the support vectors if they are linearly independent. Okay, uniquely. Now we can also generalize this result significantly, but let me skip that for the sake of time. And let me just show you how we can use this result for support recovery in mixtures of distributions. And I'll go through this very quickly. So from what we've discussed so far, we only need to devise algorithms which can recover the number of unknown vectors unknown parameter vectors having non-zero entries in all the indices of a set C that is given as input. If we can devise such an algorithm for mixtures of distributions, then we are done. Okay. So let me just show you a toy example. Suppose we have samples from a mixture of Gaussians with three components, and each of the component has mean parameters θ1, θ2, and θ3, which are known to be sparse, and each component has covariance identity. Okay. So let's also assume that these mean vectors θ1, θ2, and θ3 are sparse as well. Now, suppose we are given as input a set C, which is the first index and the second index, and we want to compute the size of S of 1 intersection S of 2, which is the number of unknown vectors, parameter vectors with non-zero entries in the first and second index. Now, in order to compute this quantity, we are going to relate it to a family of polynomials, which are known as elementary symmetric polynomials, in the variables corresponding to the square of the first and second entries of the parameter vectors. So I'll show you this. So the elementary symmetric polynomial of degree 0 is 1. The elementary symmetric polynomial of degree 1 is the sum of three terms, where each term is the square of the product of the first and second entries of each parameter vector. The elementary symmetric polynomial of degree 2 is the square of the product of the first and second parameter vectors, first and second entries of the parameter vectors taken two at a time. The elementary symmetric polynomial of degree 3 is the square of the product of the first and second entries of all the three parameter vectors. Now, if you look closely, then if the number of unknown parameter vectors having non-zero entries in both the first and second index is 0, okay, then AC1, AC2, and AC3 are all going to be 0 because each monomial in each of these polynomials has a 0 term. So the elementary symmetric polynomial with maximum degree that is non-zero is just AC0. Similarly, if the number of unknown vectors having non-zero entries in both first and second index is exactly 1, then AC0 is 1 and AC1 is also going to be non-zero because one of these monomials is going to be non-zero. Okay? But AC2 and AC3 is going to be 0. So the elementary symmetric polynomial with maximum degree that is non-zero is still going to be AC1. And if you have a similar analysis, then when the number of unknown vectors having non-zero entries in both first and second index is 2 exactly, then AC2 is the elementary symmetric polynomial with maximum degree that is non-zero. And when the number of unknown vectors having non-zero entries is 3, then AC3 is the elementary symmetric polynomial with maximum degree that is non-zero. Okay? And we can therefore conclude that the size of S of 1 intersection S of 2, which is the number of unknown parameter vectors having non-zero entries in the first and second index, is the elementary symmetric polynomial with the maximum degree that is non-zero. Okay. Which means that if we can compute the elementary symmetric polynomials in those variables, that is the square of the first and second entries of the parameter vectors up to degree 3, then we can use them to compute the size of S of 1 intersection S of 2. And in order to compute these polynomials, we can relate them to another family of polynomials known as power-sum polynomials by a very elegant set of identities known as Newton's identities. Which means that if we can compute the power-sum polynomials in the same variables up to degree 3, then we can compute the elementary symmetric polynomials, and this gives us the size of S of 1 intersection S of 2. Okay. So the power-sum polynomials look a bit nicer, I guess. The power-sum polynomial of degree 1 is again a sum of 3 terms, where each term is the square of the product of the first and second entries of each parameter vector. The power-sum polynomial of degree 2 is the fourth power of the product of the first and second entries of each parameter vector, and power-sum polynomial of degree 3 is the sixth power of the product of first and second entries of each parameter vector. Okay. And we're almost there, but I just want to point out one small detail. In the power-sum polynomial, each monomial contains only entries of a single parameter vector, whereas in the elementary symmetric polynomial, each monomial contained entries from multiple parameter vectors. Okay. And the power-sum polynomials can be estimated from the moments of the distribution. So if you, for instance, if you want to compute the power-sum polynomial of degree 1, then we can compute this quantity by using a recursive set of equations from the joint moments in the first and second entries of the random vector that is distributed according to the mixture of distributions, where the power of each of the first or second entry is at most 2. Okay. So if we know these quantities, then we can use a recursive set of equations to compute the power-sum polynomial of degree 1. So therefore, we have an outline of the process that we can follow. We can use the moments to compute the power-sum polynomials. We can use the power-sum polynomials to compute the elementary symmetric polynomials, which can then be used to compute the size of S of 1 intersection S of 2. And if we can follow this process for many subsets, then we can recover the supports of the parameter vectors. So in conclusion, we have showed mixture models with sparse latent parameters, powerful models that allow fitting complex data in data-redundant regime. And we have looked at support recovery in mixtures of distributions and provided a very generic set of techniques. And as I've mentioned, that our results in mixtures of distributions also are applicable to mixtures of many different distributions, such as Poisson, Laplace, uniform, Gaussian in high dimensions, among many others. And our techniques are also applicable to mixture models in supervised setting as well. So if you're interested in knowing more about recent results in mixture models, in hypothesis testing, signal processing, supervised setting or unsupervised setting, then please feel free to look at my thesis, mixture models in machine learning. And yeah, there's also some open problems about which I'm really excited, but let me skip them in the interest of time, I guess. Yeah, so thank you. Do you have any, please feel free to ask me any questions.
So I have a question. So you mentioned that you need three dimensions tensors for this, but are there some special cases where it's good enough to look at matrices?
Yes, exactly. That's a very good question. So under an assumption on the support vectors, we can actually matrices are sufficient. So if all the support vectors have, sorry, I mean, let me just rephrase this. If each of the support vectors has an entry that is zero in the other support vectors, but only that vector has a non-zero at that index, then we can recover the supports. Did that make sense?
Yeah. But the other condition that you gave it requires linear independence, right? For three-dimensional tensors.
Right. So we can generalize this much further. I did not go through it because I got disconnected. And so actually the condition is the following for three-dimensional tensors. We can recover the support of the unknown vectors as long as complementing all the support vectors in some fixed set of indices makes them linearly independent. Okay. So if you have the set of sparse vectors, and if you also have a set of indices where you can complement them and make them linearly independent, then you are good. You can recover them using tensors, three-dimensional tensors.
Okay. Thanks. Are there any further questions?
That's a good question. So, I think in your second last slide, where you were talking about estimating, no, maybe the next one.
Okay.
Yeah. So somehow you are taking a leap here from x1 square, x2 square to this theta1 square, theta2 square. So, but x1 square, x2 square is coming from some distribution which is parameterized by these thetas. So somehow we are going from the distribution sample from the square of that to the parameter square itself. How does that happen? Is that easy or yeah, maybe?
Great question. I had slides
Okay.
which proved it. Okay. So let me just go into the proof a bit. So since you asked this question. So if you look at the expectation of x1 square, x2 square, then I can condition on the latent variable, right? Because we have a mixture. So we can have a 1/3 in front, and we can condition on t equals to 1, t equals to 2, and t equals to 3. Okay, that is this corresponds to the component that we choose. And now remember we assume that the coordinates are independent given the latent variable. So we have the expectation of x1 square given the latent variable t and times the expectation of x2 square given the latent variable t. And now for most distributions, we can actually write this expected quantities in terms of as a polynomial in the corresponding entries of the parameter vector. Okay. So we have basically the sum of the product of the polynomials. And these polynomials has some cross terms, but if you notice, then each of the product of the polynomials are in the same parameter vector. That is, the first term is the product of the same polynomial of degree 2 in the first entry of theta1 and the second entry of theta1. And the cross terms can then be recursively computed from the other moments.
Okay. Yeah. Okay. So I guess the leap here is that somehow the expectation of the xi square, so this variance is somehow a polynomial in the theta I. I think
Right.
that's
So this condition is satisfied for most distributions.
okay.
I think I also had a hidden slide on that. Let me just let me just try to find it. Yes. So in fact, in Belkin and Sin, there is a paper by Belkin and Sinha in 2010 who shows that this condition is satisfied for most polynomials. Sorry, for most distributions, including Gaussians, uniform, gamma, Laplace, exponential, chi-square, inverse Gaussians, etc.
Okay.
For example, for Gaussians, you can represent the ith moment as a polynomial in the mean of which is exactly of degree I, and so on for other distributions as well.
Okay. Okay. Cool.
So this is a very mild assumption actually.
Yeah. Okay. Yeah. I guess here maybe maybe the thing we are assuming is that our real world comes from one of these
Right. And these are actually most distributions. I mean, this polynomial assumption is a very, very mild assumption. Most distributions satisfy this.
Yeah. Okay, cool. Yeah. Good. Okay, thanks. Yeah.
Sure.
Are there any other questions? Otherwise, let's thank the speaker.
I have a question.
Okay.
Sure.
So what do we know about the sample complexity lower bounds for these kind of problems?
That's a good question again. For support recovery, I don't have many lower bounds. The problem is new actually. I mean, I think we look at this problem specifically for the first time. But for parameter estimation, there are some lower bounds, but they do not obviously translate to support recovery. So
you're saying that for mixture of Gaussian, there are some tight lower bounds already.
for parameter estimation, yes. For a parameter estimation, yes, but not for support recovery.
Okay.
Yeah. And for the other distributions, actually, for mixtures of other distributions, there is hardly any result even for parameter estimation. Our results are actually the first ones in most distributions. For mixtures of most distributions other than Gaussian.
You're saying that for mixture of other distributions, there are no.
Most of the distributions, I think there are. Yeah.
Okay. Thanks.
In the interest of time, I think we can take future questions separately. And let's thank the speaker once more.
Thank you so much for taking out time to attend this talk.
So maybe we can talk later. You can write to me and we can talk later. You had mentioned that you wanted to discuss something.
Sure. Sounds great. I will write to you.
Okay, great.